Today we are going to discuss some more information about the distribution function. In the last class we discussed the definition, we have introduced the definition of a distribution function, its conceptual idea, and some important properties, or rather I should say some very basic properties that a distribution function must satisfy, which actually characterizes a distribution. We end last talk with an example of a function which eventually is shown to be a distribution function because it satisfies all the three properties of a distribution function that is mentioned through a theorem. Here today we are going to discuss some more important things, or rather features of a distribution function. More importantly, regarding the representation of a distribution function, or whether a distribution function can be thought of in a very general manner. By the term general manner, I want to emphasize that we can define a distribution function for a discrete random variable, we can define a distribution function for an absolutely continuous random variable. But the question is it possible to represent any distribution function in a some kind of unique way, or rather unified way? So today we are basically going to discuss this aspect of a distribution function. In continuation with the last class where we discussed some properties, rather some very basic properties of a distribution function, here we are going to discuss something more about distribution functions. Let us consider one example of a distribution function. In the last class we have considered the distribution function of an absolutely continuous random variable. Here let us see how this distribution function looks like. Now here capital F x takes the value 0 if x less than 0 equals to 1 minus p, if 0 less than equals to x less than 1, and 1 if x greater than equals to 1. Let us first look at the graph of this f x. Here as long as x is less than 0 but not equals to 0, capital F x takes the value 0. As soon as it takes the value 0, the value is becoming 1 minus 5. So there is a jump at this point. In this graph I have taken 1 minus p as 0.4. So it goes up to 0.4 or 1 minus p, and then as long as x is less than 1 starting from 0, it remains stable at 0.4, or that is 1 minus p, and as soon as x takes the value 1, there is another jump to 1, and it continues forever as long as x greater than equals to 1. So this is the graph of this distribution function, and if you check the properties of the distribution function, you will be able to see that all the four properties are being satisfied by this function f x. And from this function we can immediately see that as soon as x equals to 0, whenever, or rather whenever x equals to 0, it takes a value, there is a jump, this value is 0.4, and at x equals to 1 it takes this amount. So whenever f x, which is defined as capital X less than equals to small x, so whenever we take x equals to 1, that means probability capital X less than equals to 1, then we are just calculating the sum of these two jumps. So these two are nothing but the probabilities at the points x equals to 0 and at the point x equals to 1 respectively, and naturally it is 0 otherwise. So what we are observing here, that this distribution function shows some kind of step function, some kind of jumps at certain points. So one can think of what is the possible number of such points where we can observe the jumps. If a distribution function f has a jump of magnitude 1 at only one value, let it be c, then f is called degenerate. That means there is no other probability assigned to any other value other than c. F can take finite number of values and they are known as jumps. As we have seen in the last example, that f takes only 2 values and there are 2 jumps. F can also take countably infinite number of jumps. as an example, let us consider the geometric random variable where we can get probability capital X equals to small x, which is nothing but jump of capital F at amount of jump of capital F at x equals to small x, and it is given by 1 minus theta into theta to the power x. So, if you take x equals to 0, the jump is 1 minus theta. If we take x equals to 1, the jump is 1 minus theta into theta. If we take x equals to 2, the jump is 1 minus theta into theta square, and so on. And if we calculate the distribution function, we can immediately show that it satisfies all the three properties that we have discussed in the last class. So, now let us consider another very important concept, or rather a kind of definition, which is known as Lebesgue-Stieltjes measure. Now, this measure we are going to define in terms of distribution function in a more general way, and this has a lot of advantages that we will discuss subsequently. So, Lebesgue-Stieltjes measure, which is denoted by mu suffix capital F induced by a distribution function capital F, is a measure defined by mu of f over of a b is an interval, equals to capital F of b minus capital F of a for the interval semi open interval a to b, b side is closed. Now, the question is it possible to define this Lebesgue-Stieltjes integral for a particular for a general set other than this in the form of intervals? Fortunately, again the answer is yes, and we can define mu f of s for any Borel set S. And there comes the definition which will use this Lebesgue-Stieltjes measure mu f induced by a distribution function f. This is the definition is that a distribution function f is said to be singular, rather continuous singular, if it is continuous and if there exists a Borel set S on the real line of Lebesgue measure 0 and mu f of S equals to 1, where I just mentioned that mu f is the Lebesgue-Stieltjes measure induced by f. So, you can immediately see that the importance of defining Lebesgue-Stieltjes measure, which is induced by a distribution function, in terms of which we are going to define a particular type of distribution function which is singular. Now, what is the use of defining suddenly this kind of distribution function? Here we have a theorem. Again, this is a very important theorem in the area of distribution function. This states that every distribution function, whatever be the random variable, be it discrete, be it continuous, absolutely continuous, every distribution function f can be written as a convex combination of a discrete, a singular continuous and an absolutely continuous functions. That means, capital F equals to alpha 1 f d plus alpha 2 f s plus alpha c f c, where f d is a distribution function of a discrete variable, or rather f d is a distribution, okay, let us call it discrete distribution function, f s is a singular distribution function, f c is a absolutely continuous distribution function, and alpha 1, alpha 2 and alpha c, these are three constants, all lies between 0 and 1, so that alpha 1 plus alpha 2 plus alpha c equals to 1. Such a decomposition is unique. This is again very important, that because otherwise we might have plenty of representation of the same distribution function, but the question is, if it is unique, then our life will be very simple. Fortunately, this theorem states that such a decomposition is possible, at the same time this decomposition is unique. Now, to prove this theorem, I am not going to discuss in detail the proof of this theorem, but I will just give you the outline, which is actually given by the following lemma. This lemma says that every distribution function, we need this lemma to prove this theorem 3. Every distribution function has at most a countable number of discontinuity points, and it determines two distribution function f c and f d, such that f c is continuous and f d is a step function, and we can write f, which is any distribution function, equals to f c plus f d. So, again he is some kind of decomposition of a distribution function which is just the sum of two distribution functions, one is f d, another is f c, where f d is a step function and f c is continuous. Let us try to prove this lemma. At least I am just going to give you the outline of the proof. First, consider this interval L to L plus 1, where L equals to 0, L can take any integer value 0, plus minus 1, plus minus 2 and so on. Let us also consider that n discontinuity points of it, that are points of x f x, that lies within this interval L to L plus 1, where there is an order among them, that is x 1 less than x 2 less than x n, and these discontinuity points of f x with jumps of magnitude exceeding 1 by m. Now, remember m equals to 1, 2 and so on, m must be a positive integer. Then since we know that a distribution function is always non decreasing, we can immediately write that capital F of L less than equals to capital F of x 1 minus 0, which is less than f of x 1 and so on. Now, remember this is written because of the fact that it is right continuous. So, it might not be left continuous. So, that is why we have put the strict inequality sign here, and so on up to f of x n less than equals to f of L plus 1. Now, let us take p k, define p k as f of x k minus f of x k minus 0 for k equals to 1, 2 and so on. Therefore, we can immediately get summation p k equals to 1 to n equals to sum of this entire quantity, which in fact less than equals to capital F of L plus 1 minus capital F of L. Just a little bit of algebra using these two relations, we can get this. Thus, the number of discontinuity points of f within this interval L to L plus 1 for a fixed L of magnitude exceeding 1 by m cannot be larger than m times this quantity, that is m times f of L plus 1 minus f L, which is less than equals to m. Now, m is defined for any positive integer. So, if we let m goes to infinity, naturally the number of discontinuity points in this interval L to L plus 1 is countable. Again, since number of such intervals is countable, so we can immediately conclude that the first part of the lemma is proved, because that means it ensures that the number of discontinuity points of f is at most countable. Next, we see that p k is, suppose we define p k as p r k, which is f of r k minus f of r k minus. This means the left continuity may not be ensured, but right continuity is there because f is a distribution function, and we define capital F dx as sum of p r k, where r k less than equals to small x for any value of x belonging to real line. And if we define f c x as f x minus f d x, then it is clear that as in theorem 1, f d is non-decreasing, non-negative and right continuous. We can immediately see that capital F x is a distribution function. So, f c is also a non-negative and right continuous function. Interestingly, it is also left continuous and non-decreasing, because if we take x n less than equals to x 1 and consider f c x 1 minus f c x n, then little bit of algebra shows that this quantity is always greater than equals to 0, and it goes to 0 as x n goes to x 1. That means continuity is ensured. Now, the question of uniqueness. So, if possible, the uniqueness proving or to show that this decomposition is unique, the standard technique we will follow, which is if possible let f c prime and f d prime be other such decomposition of f if possible, then we can immediately write f c f capital F in two different ways, f c plus f d equals to f c prime plus f d prime. So, from here it is immediately obvious that f c minus f c prime equals to f d prime minus f d, but this left hand side, that is f c and f c prime both are continuous, and hence f c minus f c prime is continuous, and f d prime minus f d is a step function. So, this is not possible. So, this contradiction leads to f c minus f c prime which is equals to f d prime minus f d which is equals to 0, which immediately proves that f c must be equals to f c prime and f d must be equals to f d prime. Hence, we have proved that the decomposition is unique. So far, apart from the basic three properties of a distribution function, we have seen some examples where a distribution function is a continuous function, and we have seen an example where distribution function is like a step function. Now, whenever we are talking about a step function, whenever we see a step function, naturally we can see some jumps in some intermediate points. We have seen that there are some interesting facts about these jumps. The number of points at which one can observe this jump can be infinite, rather can be countably infinite, can be only finite values, and in some cases there may not be any such jump. Depending on that, we can term a distribution function a discrete or a continuous. Now, again, the most interesting result, I should say, is the decomposition theorem, where we have given the idea or the outline of the proof of a very important lemma, which is eventually required to prove the main theorem that a distribution function can be decomposed or can be written as a convex combination of three different types of functions. One is continuous, one is singular, another one is step function. Now, remember, this must be a convex combination. That means all the coefficients must lie between 0 and 1, and the sum of the coefficients should be equals to 1. And this comes through the lemma where it is proved that the number of discontinuity points for a distribution function can be at most countable. So, this important thing actually gives us some decomposition or the representation of any distribution function in this world, and the most important thing is that this decomposition is unique. We have also defined Lebesgue-Stieltjes measure, and in some future talks we will discuss some integrals associated with the distribution function.